Okay, so the topic for this video is simple harmonic motion. It's when an object oscillates around a certain point and will keep going unless acted on by resistive force. So looking at the example we have, you can see that there's a block attached to a spring which is attached to a wall. That dashed line is the equilibrium point, and say the floor was frictionless, if we push that block in, it'd keep moving the same distance in to the same distance out and keep oscillating between these 2 points around the equilibrium. Thus, the graph of the distance versus time, which shown below the example, would be a sine graph. So to derive a general formula for simple harmonic motion, we're going to have to use Hooke's law, which states that the force of an elastic substance, in this case a spring, would equal negative kx, x being distance, k being the spring constant, and negative just saying that the force is acting in the opposite direction of the displacement. So we start with the sigma f statement. What we want to think about is finding the distance versus time, so x of t. To do that, we set sigma f equal to mass times acceleration equal to negative kx. So we set a to be d squared x over dt squared because we want a differentiable equation if we're to find x of t. From there, you do some dividing, adding to get d squared x over dt squared equals negative k over mx. And with that, you use the guessing method. Yes, it's called the guessing method. Guess the solution. And you'll get x of t equals a sine theta. And because we have from before that the w, or the angular velocity, equals d theta over dt, theta being angle, we can derive that theta equals wt. So such, x of t equals a sine of omega t, the w is omega. So we set that equal to dx over dt, a w cosine wt. So you get that by taking the derivative of the function we guessed before. And when you take the second derivative, you get negative a w squared sine of omega t. That a is a constant. It's simply a constant, and we'll find it later. So by using this, we can see that d squared x over dt squared equals negative w squared x. Now using both of these, you will notice that k over m is equal to w squared. With that, you can say, you can set them equal now and get w equals square root of k over m, elastic constant over m. And the general form, going back to the d squared x over dt squared equals negative k over mx, if the general form of simple harmonic motion is defined as d squared x over dt squared plus k over mx equals 0. So next we're going to look at how it's for angular frequencies period. So we're comparing those two. If you notice, theta, the whole period, would be 2 pi. And as we found in the last part, theta equals wt, or omega t. So when you solve through, you get t equals 2 pi over w, omega, and t would be the period because 2 pi is the full revolution, and t is the time it takes to make that full revolution. So the period is how long it takes for an object to do a full oscillation or revolution. So the period would be 2 pi over d. Now that we know how the forces worked, we should look at the energy in these systems. So for this, we'll specifically be looking at an object going in has only horizontal movement. And so an object would have 2 types of energy, kinetic energy and elastic potential. So to find the specific kinetic energy for the example we looked at with the object attached to a spring attached to a wall, we'll start with the formula 1/2 mv squared. So we use the fact that we know that v equals omega a cosine of omega t whole squared, because wr equals v. And with that, we now simplify to get 1/2 m omega squared a squared cosine squared omega t. And we know that w equals square root of k over m, so we substitute that in for w squared to get 1/2 m k over m a squared cosine squared wt. And with that, we get 1/2 k a squared cosine squared of omega t. With elastic potential, we start with the general formula 1/2 kx squared, x being distance. And we solve for that. X of t would be the distance we have. So it'd be 1/2 k a sine of omega t whole squared. With that, we get 1/2 ka squared sine squared wt. Now, TME is total mechanical energy in the system. And because it's frictionless and no outside work is being done, it would be kinetic energy plus elastic potential energy. With that, if you combine them, you'll get a very simplified and nice looking answer, 1/2 ka squared. And so what we looked at before, or initially in our example, was a horizontal spring oscillator. So it's an object attached to a spring attached to a wall. So it'll move left and right. And with that, we know the general form is d squared x over dt squared plus k over mx equals 0. We derive that from the force equals mass times acceleration. But what we can find is by using the equation we got of x of t, so the distance equals a cosine of wt plus phi, we can solve through and we'll get that the period squared equals 4 pi squared m over k. The period, one period, would be 2 pi square root of m over k. But in this case, we want to look at the relationship of t squared because we want a linear graph. We're linearizing it. Now the second that it could be is vertical. So a spring that goes up and down, since it's attached to the ceiling, it'll oscillate up and down. So to derive what the net force would be, we get the force of gravity minus the force of the spring, because the force of gravity is acting down on the object, and because the spring force is acting in the opposite direction of its displacement, it's acting up. It's a resistive force now. Instead of having friction in the above example being the resistive force, the force is now the resistive force, the elastic force. So with that, we get mg minus ky, y being the displacement in the y direction, equals m times the acceleration in the y direction. And we get that F net equals negative ka by solving for y at the equilibrium. Y at the equilibrium would be mg over k because the acceleration would be 0. And by plugging that in, you'll find that it's negative ka, F net. So the last portion of this lesson before we get into the examples would be springs in series and in parallel. So in series, that's when you have one spring connected to another spring connected to an object. And with that, you have to use the equation, the force equals negative k1, so the coefficient of the spring, the spring constant of the first spring, times the distance of the first spring that it does, equals the negative spring constant of the second times the distance of the second. So with that, both springs are equal. In this case, the force acting is equal. So you can solve for x1. And then we plug that in to an equation where we have F net equals negative k equilibrium, equivalent, not equilibrium, the equivalent spring constant times both distances added, x1 and x2, equals k1 x1 plus k2 x2. With that, you'll get an interesting equation because it'll remind you of resistors in a parallel. So it would be 1 over k equivalent equals 1 over k1 plus 1 over k2. It also is like a capacitor in series. Now the parallel is the opposite. So that's when you have one spring on top, the other spring on the bottom. K1 could be top, K2 could be bottom. So F net equals K1 times X plus K2 times X. So the X's in this case are the same, the distance of the spring, how long the spring is, they're the same. So that would equal K1 plus K2 times X, and which equals the K equivalent times X. And so you get K equivalent equals K1 plus K2. That's like the resistors in series and a capacitor in parallel.
Okay, so now for our example problem, we chose 2003 M2. And the problem reads, an ideal spring is hung from the ceiling and a pan of mass M is suspended from the end of the spring, stretching it a distance d as shown. A piece of clay, also of mass M, is then dropped from a height h onto the pan and sticks to it. Express all algebraic answers in terms of the given quantities and fundamental constants. And Part A asks to determine the speed of the clay at the instant it hits the pan. So our answer, we decided to solve it in terms of energy because we realized that there was a conservation of energy in this situation. So we used gravitational potential energy and kinetic energy, and so which would equal mgh and 1/2 mv squared. Then we manipulated the equation to eventually get that the final velocity would equal the square root of 2gh. For part B, it asks to determine the speed of the pan just after the clay strikes it. So for this one, we decided that we should use the momentum, and since we realized that momentum was conserved. So basically we have mv initial equals mv final, but since the final mass of the situation is both the mass of the pan and of the clay, it would be 2m. So we have the original mass m times the original velocity is equal to 2m times the velocity of the pan and the clay combined. Again, we manipulated that equation to eventually get that the final velocity after the two had collided would be 1/2 times the square root of 2gh. Then after that we reach part C, which asks us to determine the period of the simple harmonic motion. And so basically for that, we already found that the period for a mass on a spring would be t equals 2 pi times the square root of m over k, which was earlier seen as t squared in our diagrams, because in order to graph it linearly you need to square the period. But in order to manipulate that equation to get what we need, the m would obviously not just be a random mass value. It would be the mass of both the pan and the clay after the collision. So we substituted in 2m for what was previously the lowercase m. So then after that, we wrote out a force equation. So we have F equals ma, and since acceleration would equal 0, you can set mg equal to kd, d being the displaced distance. Then we solve for k, and k would equal mg over d. Then we just plug the k value back into the original period equation that we made. So it would be t equals 2 pi times the square root of 2d over g. Next, part D asks to determine the distance the spring is stretched from its initial unstretched length at the moment the speed of the pan is a maximum, and to justify your answer. So basically for this, we decided that with the spring the way it is with the weight on it, it reaches almost a new equilibrium point, so we decided to take it from that equilibrium point rather than trying to expand on the original equilibrium point. So we again wrote out a force equation. So force equals the mass times acceleration, but at equilibrium acceleration would equal 0. So we were able to set 2 mg, which is the mass after the collision, equal to kx, x again being the distance of displacement, which would be the maximum distance away from the equilibrium point in our second scenario with the mass already added to it. Again, we manipulated the equation and we plugged in our k value, which we found in part C, and we ultimately got 2d is equal to x, which would be the distance that the spring is stretched after the pan reaches its maximum amount of stretch. And then finally we have part E, which states that the clay is now removed from the pan and the pan is returned to equilibrium at the end of the spring. A rubber ball, also of mass m, is dropped from the same height h onto the pan, and after the collision is caught in midair before hitting anything else. Indicate below whether the period of the resulting simple harmonic motion of the pan is greater, less than, or the same as it was in part C. And basically what we said is that it was less than it was in part C because of the fact that the mass would be smaller in this situation rather than the situation in part C, and relating it back to our period equation, the smaller the mass is, the smaller the overall period value would be, so therefore the period value would be less than it was before.